Why is nitric acid such a powerful acid? We know that it has one proton that readily dissociates to form this nitrate anion, but as you saw in the previous video, the protonated form of nitric acid has a pretty respectable resonance system, which would tend to make this then a very stable inert compound. So why should this be so motivated, so to speak, to lose its proton? So what we have to do in this video is examine the resonance structure of the nitrate anion. And remember, we have this covalent bond here, and that covalent bond did affect some of the resonance structures. So in this video, we're going to really draw upon the knowledge of the previous video when we're considering resonance structures of the nitrate anion. So its basic structure is coordinate bond here, a double bond to oxygen, a sigma bond to this oxygen, which now has a negative charge because it lost the hydrogen, and this now has a lone pair of pi electrons. So what you can imagine happening, if you've watched all the previous videos in this series, is this oxygen keeps both pi electrons that are in that bond, and then this lone pair of pi electrons comes in to form the double bond with nitrogen. So one resonance structure looks like this. The coordinate bond is here. This will have a negative charge. With a lone pair of pi electrons that it confiscated from that pi bond, and then a double bond with this oxygen. This oxygen had a negative charge, but it put up both pairs of electrons to form this bond, so now it has no charge. So that's one resonance structure. Now, as you saw in the previous, well, before we say that, let's look at this. Here, what we can do is we have oxygen with a double bond here, the single bond to this negatively charged oxygen that now has a lone pair of pi electrons. As we showed in the previous video, now what we can do is, and we discussed this at length in the previous video, so we're not going to discuss it in great detail here, but instead the coordinate bond comes to here with this oxygen with no electrical charge, and a single sigma bond to this oxygen, which now has a negative charge and a lone pair of pi electrons. And why it should be like that, again, we explained that in the previous video, so that is nothing new. And then we have the double bond to oxygen. Now, what can happen here is that this oxygen can keep both electron pairs for itself, and this one can donate the electron pair to form the double bond. So now we will have this resonance structure. Nitrogen, double bond to here, and the coordinate bond like this. Notice that these structures here, going from, let's get rid of the arrows now, we don't need them. It'll just be confusing. Notice that these are symmetrical. Here, this oxygen had a negative charge. Now it's this oxygen that has the negative charge, and the double bond the double bond between nitrogen and oxygen is between nitrogen and oxygen. So those are symmetrical. Notice also there's no charge separation that we had in the previous video when the nitric acid was carrying a proton. We have charge dispersion. That's a superior resonance system. And now notice here that these structures here are also symmetrical. Before, this oxygen had the negative charge and the coordinate bond was here. Now that has the negative charge and the coordinate bond was here. Just as if we just rotated this 180 degrees. So those are symmetrical. Notice here, these, try to keep all of them in focus if we can. These here are also symmetrical. Here, the double bond is here. Now it's on the left side. The single bond to a negative oxygen on the left side. Now it's over on the right side, as if this had just been flipped over. So again, we have symmetry. Now, what we can imagine is, just as we did right here, negatively charged oxygen, coordinate bond, it changes position. Again, we discussed that in length in the previous video. Now that can happen here. This will have the coordinate bond, and this will be back to having a negative charge. So now we have nitrogen. We're going to need a little bit more room here. Coordinate bond to this oxygen. Lone electron pair, negative charge on that oxygen. Again, we explained that in more detail in the previous video, and our double bond to oxygen. Notice that these are symmetrical. Here we had negative charge oxygen, coordinate bond. Now the negative charge oxygen is here, the coordinate bond is up here, just as if this has been flipped over. So this is symmetrical. Now, let's compare this. We can get these in focus at the same time. Okay, let's compare this structure with this structure. Again, these are also symmetrical. Here, the coordinate bond is to the left, double bond on the right. Here, double bond on the left, coordinate bond on the right. So these are also symmetrical. So far, every single, I don't know if we get them all in focus at the same time, but every single canonical form that we have wrote out so far, all of them are symmetrical with one another. And all of them are involving dispersion of negative charge, no separation of positive and negative charge as what we had when this was protonated. And then finally, there's one more thing that we can do. We have enough room to do it. Here we have nitrogen. Coordinate bond to this oxygen. Only now here, for this resonance structure, this lone electron pi, there. Well, this oxygen keeps both pi electrons. This one, which now had a lone pi pair of electrons, comes in to form the double bond. So we have this negative charge here, and now a double bond here. This had a negative charge, but it put up both electrons to form that pi bond to get the double bond with oxygen, so that has no charge, and this has a lone pair of pi electrons. Now let's take these arrows out because they can be kind of confusing. And let's compare these two structures. Here, double bond at the bottom, single negative charge at the top. Here they're just switched around. Those are symmetrical. Now let's compare this one and this one. Here, double bond at the bottom, coordinate bond to the left, single negative charge, single bond to the right. Same thing here, except this is on the right and that's on the left. That has been flipped around. These canonical forms are also symmetrical. So, when nitric acid loses its single proton to form this nitrate anion, I don't know, can we get all of these in focus at the same time? It's about as good as it's going to get, I guess. Notice we have 1, 2, 3, 4, 5, 6 canonical structures that we can draw. They're all symmetrical with one another. There's no separation of charges. That's supposed to be oxygen. There's no separation of charges. Instead, what we have is charge dispersion. This is a very, very powerful resonance system. So even though, as you saw in the previous video, the protonated form of nitric acid did have a respectable resonance, nonetheless it is still highly motivated to get rid of that single proton, form the nitrate anion, where we have this marvelously powerful resonance stabilization right here with these 6 canonical structures, charge dispersion, and all of them are symmetrical with one another. So that is why nitric acid is such a powerful acid. Okay, I think that wraps it up for this video. Remember, the playlist for all the videos is at the website at digital-university.org.